Okay, so let's talk about derivatives. Okay, many of the concepts that we have been seeing so far in the course lead to this point. Okay, derivatives are a fundamental concept in calculus because they study how function changes around the point or is varying across the point. Okay, so let me um, give you some idea about this. So suppose we have a function f, right? Something like this, and we want to know. Suppose it's like the speed of a vehicle, position, something like that, and we want to know how this function changes in time or in as a function of us is variable, right? So one way of thinking about this is we have f at x1, right? And then we have f at x2, and we want to say, well, in this difference in between x1 and x2, right, this function has changed this much, right? So in this interval x2 minus x1, this function has changed this much, right? So this is f of x2 minus f of x1, right? And we typically represent this like this: delta. This is the Greek letter delta, but the capital one, right? And then delta f with respect to x, the increase in x relative to the increase in the variable, right? So this is f of x2 minus f of x1 divided by x2 minus x1, right? But it's clear, and so that's given by the slope of this line, right? So we have this line. This division is actually the tangent of this angle, right? So this divided by this is the tangent of this, which is the slope of this line, right? But it's clear that if we, instead of choosing x2 and x1, we choose a different point. For instance, let's say x3, right? Between x2 and x1, the slope is going to be different, right? The difference change between one and the other is going to be different, right? So in math, what we want to study is how is this rate of change at this particular point, x1, right? And in order to do that, we want to get closer and closer to it, right? So if we want to get these triangles as we want, get closer and closer to it, so we get like the true tangent of this curve, right? This slope of change at that particular point, okay? And that, in order to do that, we need to use limits, okay? And so that's what the definition here does, right? The derivative of a function f, right? It's that rate of change of that function at a point a, right? And it's given by this f prime, right? Of at a is the limit when x goes to a of this quotient. That's the idea that we have been saying, right? F of x minus f of a divided by x minus a, provided this limit exists. Sometimes it will not exist. Okay, when the limit exists, we say that the function is differentiable at a, right? We could also define the derivative as the limit when h goes to 0 of f of x plus a plus h minus f of a divided by h, right? And in this case, what we have said is introduce the limit x is equal to a plus h, right? And when x goes to h, x goes to a, h has to go to 0. Okay, so this definition is equivalent to the other one, right? And so the idea of this is that this derivative is the tangent, okay, the value of the tangent of the curve, okay, this, well, not the tangent, the slope of this tangent, at this particular point. Okay, so that's a very important geometric way of understanding the derivative. You have any function, the derivative of this function at that point is the slope of the tangent, which is the line that touches the function at that point but doesn't cross it. Okay, and also this is the standard way of writing the derivative in calculus 1 courses, but we also sometimes use Leibniz notation, right? So this is Leibniz notation, which kind of fell out of use in some parts of math, but it's actually pretty intuitive, because the idea that Leibniz had was that we were taking very small increments in x and seeing how these increments in f corresponded, right? So this you get the idea of very small increments both in x and f, right? But the idea is that this is not rigorous enough, because you can't define very small increments, because you can always get some smaller increment, right? Because of the properties of the real numbers. Okay, so let's compute some derivatives, okay? To get some examples. We have, let's see what's the derivative of x squared, okay? Well, f prime at a, right, this is the limit when h goes to 0 of f at a plus h minus f at a divided by but f of a plus h is a plus h squared, and this is just a squared. So this is the limit when h goes to 0 of a squared plus h squared plus 2ah minus a squared, right, divided by h. So this and this cancel out, and then we have the limit when h goes to 0 of h plus 2a, or in other words 2a. Okay, now because this is true for every a, right, we can rewrite this like this: the derivative of x squared at x is 2x, as you will probably know. Okay, an exercise for you is to derive the derivative of f of x equals x to the n, where n is a natural number. So derive that this is equal to this, the f prime is n times x to the n minus 1, using Newton's binomial formula. Okay, remember that Newton's binomial formula is let's see, x plus y to the n, right, is equal to the sum from k equals 0 to the n of n over k, and this is the binomial coefficients of x to the k, y to the n minus k. Okay, let me write this later. Okay, you have to use this one and prove that this is true, right? Okay, so now let's see another functions. Let's see, we have the sine and the cosine, right? Well, what's the derivative of the sine? Is the limit when h goes to 0 of the sine of x plus h minus the sine of x, right, divided by h. Well, this is the limit when h goes to 0, and then the sine of x plus h, we can use the formula for the sum of the sine of the angle, sorry. So this is the sine of x times the cosine of h plus the sine of h times the cosine of x minus the sine of h divided by h, right? And so this is, let me see, we have the cosine of x times the limit when h goes to 0 of the sine of h divided by h, and then plus the sine, wait a minute, sorry, this is no, we don't need. So then we have sine of x. Is this correct? Yes. Oh, yes. Sorry. Yeah, that's the problem. This is the sine of x and not the sine of h. Okay. Now we have the cosine of x that multiplies the limit when h goes to 0 of the sine of h divided by h, and then we have the sine of x that multiplies the limit when h goes to 0 of the cosine of h minus 1, sorry, minus 1 divided by h, right? We're just taking common factors out of the limit. Okay, now the limit of this is going to be 1, we know that. The limit of when h goes to 0, the sine of h divided by h is 1. The limit of this is going to be 0 because we know that the cosine of h minus 1 is approximately equal to h squared divided by 2, right? And so this is h squared divided by h, you get h divided by 2, which is 0, okay? So this part is going to be 0. So the result of this is the cosine. Now if you do the same with the derivative of the cosine, what you get is the limit when h goes to 0 of the cosine of x plus h minus the cosine of x divided by h, the limit when h goes to 0, and then the formula for the sum of the cosine of the sum is cosine of x times cosine of h minus sine of h minus the cosine of x divided by h, and this is similarly we get the limit when h goes to 0 of, and then we have the cosine of h minus 1 divided by h times the cosine minus, and then the limit of h when h goes to 0 of the sine of h divided by h multiplying the sine of h. This goes to 0 as before, this goes to 1, so this is minus the sine of x, okay? So the derivative of the sine is the cosine, the derivative of the cosine is minus the sine, as probably most of you knew. Okay, let's do the exponential. Okay, so the exponential is f of x e to the x. F prime is the limit when h goes to 0 of e to the x plus h minus e to the x divided by h. But then we can get common factor e to the x here, gets out. The limit when h goes to 0 of e to the h minus 1 divided by h, but we know that this is 1, so this is e to the x. Okay, that's why the derivative of e to the x is the same function, and that's the only function actually that has this property. Okay, that's a very interesting one. Okay, so we have that derivatives for a lot of our basic functions. We say that a function, if a function is differentiable in an interval, right? For every point in an interval, we say that the function is differentiable in that interval, right? And then we can define the derivative function. Okay, so then we have f prime, which is a function itself, right? As you have been seeing, that assigns to each point in a domain, it's the derivative of f, right? And it works, the domain of f prime is going to be those points where f is differentiable, okay? So that's the derivative of f. And also we can do this recursively and define the second derivative of f, which is assigns to each point in its domain, which are those points in which this function is itself differentiable, right? f prime at x is the limit when h goes to 0 of f prime of x plus h minus f prime at x divided by h, right? So it's always going to be the same, right? The second derivative is the derivative of the derivative. Then we can have the third derivative, the fourth derivative, and so on, right? The third derivative is the derivative of the second derivative. The fourth derivative is the derivative of the third derivative, and so on, right? Up until the fourth derivative, or maybe including this one, it's typical to write them like this: f to the parentheses, okay? And then this implies the nth derivative, okay? So then if you have f4 like that, that's the fourth derivative, okay? Fourth derivative, right? Okay, so next, this is a very important theorem, okay? If f is differentiable, right, then at a, it is also continuous at a, and it's also very simple to prove it, right? Well, what we need to prove is that the limit when x goes to a of f is the limit is f of a, that means that f is continuous, right? Is, let's see, sorry, what we have to do is that if, wait a minute, let me, if f is differentiable at a, that means that the limit when x goes to a of f x minus f a divided by x minus a exists, okay? Let's call it f prime at a. This exists, and we need to imply, to prove that this implies that this limit exists and is equal to f of a, right? But this is equal to saying that this difference, right, is 0, right? Or well, it doesn't matter the absolute value or not, right? So let's see, what can we say about this difference? Well, the limit when x goes to a of f of x minus f of a, right? And then we're gonna multiply and divide by x minus a, right? So then we have the limit when x goes to a of f of x minus f of a divided by x minus a multiplied by x minus a. Now this thing exists, is the derivative, so we can say that this is the limit when x goes to a of x minus a, right? That multiplies the derivative. Now the derivative is finite, and this limit is 0, right? So 0 times something that's finite is going to be 0, which is what we wanted to prove. Okay? So it's a very important theorem, and a very important consequence of this is that functions that are discontinuous, okay, will not be differentiable at the discontinuities, right? But another way of saying this is that if f is differentiable at a, it is also continuous at a. The other implication is not true, okay? If f is continuous at a, it doesn't have to be differentiable at a. Okay, typical example for this is the absolute value. Okay, the absolute value is continuous in R, right? But it is not differentiable at 0, right? If we compute the limit when x goes to 0 from the right of this x minus 0, right? Well, from the right this is 1, right? Because this is x when x is positive. If you compute it from the left, when x is negative, the absolute value is minus x, so the limit of this is minus x divided by x minus 1, okay? This is not equal, so that means that the limit doesn't exist, okay? And so this is the absolute value function, right? This means that at this point the function is not differentiable. One way of saying this or seeing this graphically is when a function is not differentiable at a point, it's you can see a spike, okay, something like that, okay, point, okay, a kind of cusp in this function, right? And so yeah, there are some other functions that you can try and prove that they're not differentiable. For instance, f of x, x times the sine of 1 over x if x is different than 0, or 0 if x is equal to 0. Well, this function is continuous because you can compute the limit when x times the sine of 1 over x goes to 0, and it's 0, right? But now if we compute the limit when x goes to 0 of x times the sine of 1 over x minus 0 divided by x minus 0, this is equal to the limit when x goes to 0 of the sine of 1 over x, and we know that this is doesn't exist. Okay, if the limit doesn't exist, the function is not differentiable at that point. Okay, that's the end of this